you guys have that. When you're looking at a fireworks show, like on the screen, you are seeing different colors of fireworks, not because of food coloring, not because of CGI, but there are different elements that are burning in combustion reactions. Different elements burn different colors. So that is something else I wanted to show you is this. Have you ever seen these types of candles? These are candles that are sold specially. They're not normal candles, but they're sold specially, and they are purported to have different flame colors. Just like fireworks have different colors, these candles also have different colors, or purported to. I'm going to test them right now. How do they have different colors? Same reason. They're different elements in the periodic table. They're different elements have different colors that they burn when you put it in a combustion reaction. So let's test it out. So let's get these candles, and you can see I've used them before, but they're different colors. And so the orange is supposed to be an orange flame. The blue is supposed to be a blue flame. So let's try this blue one. Let's start with this blue one. I'm going to light this on fire. And let's see, it's a blue candle, supposed to have a blue flame. Got to light this first. Okay, let's wait for it to take. And do you see a blue flame? No, it's way too bright to see anything. Let me see if I can get closer there. So I see kind of an orangish flame. Oop, it's way too bright to see anything. Let's try this angle. Okay. So I see kind of orangish flame with a very low blue. Let me try to shield that. So it's an orangish flame with a very low amount of blue. Let's blow that out. Not useful. Let's try this purple one, though. The purple candle. So here's a purple candle, and I'm going to light it. And you guys will soon see why though I'm doing this at home, I also recorded this at SMC at lab so that experiment actually worked. But you will see that experiments, you got to try them out before you figure out they work or don't work. So this one's the purple flame, and it is also way too low to see. It's kind of an orange, giving off an orange glow right now, but it is actually very, very lightly purple. Very lightly. Not too exciting, huh? All right, then let's try the orange candle. So the orange candle is supposed to have an orange flame. So I'm lighting this orange candle, and let's see what you get. Now, all the other colors have been orange, so I wouldn't be surprised if this one is orange. So here we go. Orange candle. Is this going to give us the orange flame? So we do have an orange flame coming out of here. Let's see if I can shield some of this. You see that orange flame, orange candle, orange flame. Now you might be thinking, what's the big deal? Fire is orange already. So yeah, if you see these, and put it back in the box, rainbow moments, expensive candles purported to have the different colors. Well, don't trust it. For one, they're expensive. For two, you're burning different elements. They're supposed to have the different colors. Perhaps if it were upright and burning for a little bit longer down, you would see the green and the orange and the blue and the purple. But the thing is the elements, the different elements are elements that will end up on that cake. And so you don't want that. So many reasons to not buy that, not buy that. Okay, so let's switch over though to some slides. Okay, so for this week's lab, make sure you already have the lab report. You guys want to have already downloaded the lab report, printed it out, finding this. And you can copy or you can write down notes on the lab procedure and the lab report as you are taking notes. I'm going through the slides. So My recommendation is make sure you are, is this working? Can you guys see that? Okay, make sure you're taking notes on the lab procedure. These slides are correlated to go along with what you have in your lab procedure. And then I will also continue on to showing you sections during the lab of the procedure and also the lab report. And we're going to work on the lab report. The other thing we're going to do is make sure you have time to complete the simulation. There's a video, it's not a simulation, it's a video assignment that's, you'll see. It's a video assignment that is a video assignment similar to the first one you did where you'll answer questions during the assignment. So we'll have time to complete the lab report and the video assignment during today's lab section. So back to this. This is flame tests that are actually going to work. And this is showing those fireworks. So when you see yellow fireworks or purple or green, they're different elements in the periodic table. Yellow is actually sodium. Sodium, the element symbol Na. Okay, or green. Green is copper. Copper, the element symbol Cu. And so you are looking at different elements in the periodic table. And in this, we are reviewing also energy in the electromagnetic spectrum and calculations for electromagnetic radiation with wavelength, frequency, and energy. So this is the electromagnetic spectrum. You've seen this before. And we have all different types of energy that is radiation. And some of this radiation is low energy and some is high energy. And remember, what you want to do is orient which side is the low energy side and which side is the high energy side. So when you see this, you can find always the low energy side is radio waves. So these are the low energy waves on this side, and gamma rays. The gamma rays are always going to be the high energy side. So the low energy side includes everything from visible light on down. This is non-ionizing. And so this was in last week's discussion that there's all different types of radiation. Some radiation is dangerous, but most types of radiation in the electromagnetic spectrum are not dangerous because they are non-ionizing. They don't have enough energy to break bonds in molecules. And so that's visible light, infrared, microwaves, radio waves, and everything in between. So also in there are cellular data, Wi-Fi, the phones in your house. If you walk around with the phone in your house, those are portable phones. Anything that is in your house is basically low energy, non-ionizing, and it's not going to be dangerous, including those microwaves that we talked about in lecture. But then you have the higher energy. So this is above visible light. These guys are ionizing radiation. And ionizing radiation these are high enough energy to break bonds in molecules. That includes UV from sunlight. And that's what we are exposed to for the most part, is that small amount of UV. And we will be talking about exactly how you protect yourself from UV. We talked about it in lecture, but we're going to continue on with that with next week's lab. So, but this week's lab, we're still talking about radiation. And so there's also X-rays and gamma rays are high energy that you are generally not exposed to. X-rays you are exposed to in controlled amounts. Your doctor, your dentist keeps track of how many X-rays you're allowed per year or even every other year. And gamma rays you're not exposed to. Those are really only going to come from a nuclear explosion, which doesn't happen. But we will talk about when that does, when there are cases of nuclear energy. This is nuclear energy that we'll get to in module 6 that does have gamma rays and that type of radiation. So let's focus now on the visible light. So down here is the visible light spectrum. So visible light is broken out. Okay, and that's usually roughly in the middle of the spectrum. So this is also listed from low energy to high energy. You want to find the low energy side and the high energy side. So just as it is on the right, this is low energy over here, and this is high energy over on the left. So it's still listed from high down to low. And the low energy color, the lowest energy color is red, compared to the highest energy color is violet. And so you have all the colors in between, and the colors are the only ones we can see on the entire spectrum. We can see visible light. That's why it's called visible light. And we can't see any of the other things. You can't see X-rays. You can't see infrared. You can't see microwaves. But these seem different to our senses in different ways. For instance, infrared is heat, and we can feel infrared, okay? Or UV is high enough energy to break bonds, and that does have effects on the body, beneficial and harmful. And so we can have that those effects with like sunburn, suntan, aging, wrinkles, skin cancer from UV. Okay, so but what the main type, for all these different types of energy, these are going to be types of energy that differ in the amount of energy, low energy versus high energy, and everything in between. And also wavelength, which, remember, the symbol is this upside down Y, that's called lambda. And they also differ in frequency. The symbol for frequency is that kind of cursive V, that's called nu. So you want to get used to those symbols, because we're going to use those in calculations. We've already used them, but we're going to get more practice with them today. So wavelength, frequency, and energy. We have on the next slide, properties of waves. So wavelength, let's write that again, is the symbol wavelength is that upside down Y, lambda. And the definition of wavelength, it is the distance between equal parts of a wave. So if I draw a wave here, this is going to be a wave, and the wave continues in space in both directions. So there's an arrow on either side. So the distance between equal parts, like peak to peak or trough to trough, this would be one wavelength. Okay, and this is going to be in meters or M. Frequency is that symbol nu, and frequency is how many of these waves pass through a point in 1 second. Okay, so you basically choose one point. Let's make this a different color. I'm going to choose this point here, and I count how many waves go through in 1 second. And so this is in units of 1 over s, or also s to the -1, or Hz, which is hertz. They are all equivalent. And so you will see that the most useful that we use is this one, 1 over s, because that 1 over s, the second, will cancel out. And so we want to use this one when you are doing calculations. Now, energy is just the uppercase E. Thank God, because there's too much going on with these Greek alphabets. So the energy of a wave that we can calculate in these equations. So you have two equations that are used in these calculations. And this one is wavelength times frequency is equal to c. So let's add these other constants. So these are the constants. One is the speed of light, which you always have. That's c, and that's 3 times 10 to the 8th meters per second. And then you also have Planck's constant. Oops, let me spell that correctly. So that's Planck's constant, P-L-A-N-C-K. You don't have to spell it correctly, but I do, which is H. Now, this is another thing about these electromagnetic calculations. All these letters, you got the Greek letters, and then you got the speed of light is C. I don't know why it's C, it's not S. And then you got Planck's constant, which is H. I don't know why. The other letters were taken, let's just say that. So you have Planck's constant, which is a constant value, just like the speed of light is a constant. You will always be given it. The thing is you have to recognize that it is a variable, it's a letter. And so you might think like it's an unknown, but it is not. It's a known value. It is the constant 6.63 times 10 to the minus 34, and the units are J times S. That J stands for joules. And those are the units of energy in joules. That's that uppercase J. And joules are 1 unit of energy. They're the units of energy that we use in calculations for electromagnetic radiation, just like this is the preferred unit for frequency, though you can use, you'll see it as S to the minus 1 or hertz. Joules are the units for energy that are calculated using this equation down here. When you calculate energy using this equation, it ends up being in the units of joules because of Planck's constant having joules times seconds. So the units for energy don't have to be joules. We will see in a later module that units of energy can be also calories, and that's when we're talking about nutritional energy. So we will be using joules though in this calculation. So in these two equations, you have these two are constants, and these are constants. And one thing to remember about constants is that they are infinitely significant. So infinitely significant means that these you're not going to look at for sig figs. So don't look at these for sig figs. Because they are infinitely significant, this 3 does not have 1 sig fig. It's infinitely significant. Or this 6.63, you might say, oh, that's 3 significant figures, but it's not. It's infinitely significant. All constants or numbers in an equation that are already there, or conversion factors, those are all infinitely significant. Why? Because they're not measured values. Only measured values have significant figures. And so that's what we'll be focusing on is, what do I need to round off? Where do I look? You're always going to be looking at the measured values, and those are usually the numbers that are given in a word equation. So actually, I'm going to get my calculator ready. Even though I'm not going to calculate anything just yet, I'm getting my calculator ready. So I have this here. So the properties of waves are related in this first equation. This is wavelength and frequency are multiplied together, and multiplied together always have to be equal to this number, the speed of light. So when these two numbers, the wavelength and the frequency, have to be multiplied together and always equal to the same exact number, this forces them to have a relationship which is inversely proportional. So inversely proportional means that opposite. If the wavelength is high, the frequency is low. If the wavelength is low, the frequency is high. So this upper wave is an example of having a big distance between the wave troughs. So this is a high or a long wavelength. You have a lot of space between those waves. And what you have is a low frequency. You don't have very many of those waves passing through the point in 1 second. This compares to this wave. So this wave, which I could keep on going in either direction, this has a wavelength here, and this has a low or short wavelength. Not much distance between those waves. And as a result, when you take one point here and you count how many waves pass through 1 second, that has a high frequency. You got a lot of those waves passing through the point in 1 second. So they're inversely proportional. This other equation, this is a relationship between energy and frequency. So this is basically frequency is directly proportional to energy. So directly proportional, that means the same. So this is a low frequency, like this one up here. This is a low frequency. A low frequency, not many waves passing through in 1 second, will also have a low energy. Or this one, this high frequency, a lot of waves passing through this point, that will have a high energy. And so the calculations we can do now that we hopefully understand the relationships between energy, wavelength, and frequency. Okay, so let's take a look. I want to go back to here though, is that you also have this on this slide, is that you can see the differences between these waves that the gamma rays. So these are high energy, a high value for E. There's also a high frequency. You would have a lot of those waves passing through one point in a second. And then you would also have a low wavelength using those, get used to those symbols. And then on this other side, you can see the radio waves. The radio waves we know are low energy, so a low value for E. And then you have a wavelength, they're more spaced apart. So this is a high wavelength, and you don't have as many of those waves passing through a point in 1 second, a low frequency. So these are the ionizing versus non-ionizing radiation. Hopefully you guys are definitely good on that and starting to talk to people around you about microwaves, radio waves, and including things like Wi-Fi or standing next to a cell phone tower. Would you do that? Of course. Those are all non-ionizing radiation. Though they may look scary, they're not. They are low enough energy. And so in last week's discussion, it was about UVC. And so you guys saw that UVC is higher energy and used to, because it can break bonds and molecules, it can be used to sanitize surfaces, but only when people are not around. So it's good to do it at night when cleaning a room, and then just shine some UV light, and that'll get even more bacteria and microbes with this basically zapping process, killing these things by breaking the bonds in those molecules. Okay, so this is what we're getting to, is in the lab today, we're going to be looking at flame tests that actually work, unlike the candles I just showed you. You're going to see different colors of flames, and these are 3 examples. So you see red. This is easy. This is the dominant color is red. So you're going to be looking for a dominant color. And here is, hey, that one's blue. Those are easy. So you're going to relate a dominant color to a wavelength value, and this wavelength value is going to be reported in nanometers. So nanometers, remember nm is nanometers, and that's the metric prefix, which is n 10 to the minus 9. So when you have a red, that's 701 nanometers, that's 701 times 10 to the minus 9 meters. Okay. But back to the dominant color. The idea of the dominant color is that you want to report the major color you see. So in this flame has mostly the dominant color. Most of it is either, you could say, orange or orange yellow. You don't want to be too creative because you want to go with the colors that are in this listing, this table. And this is the same table that you have in your lab procedure. So orange, or you could write orange yellow, but you don't necessarily want to say this top part of it is red. So the top part is the red orange, but you don't want to go with something that is the minor color. Okay, so you want to go with the dominant color, the majority of the flame. The other thing we're going to be seeing in these flame tests is that the flame goes out kind of quickly for some samples. So you want to catch the first color you see that is not the flame itself. There's going to be a blue flame from the Bunsen burner, and then there's going to be the sample I test. So for some of them, I'm going to pause so you can really get that, that flame test color. Or if you're watching this on video, you're going to pause that video. You got to catch the flame test. Sometimes it's only 1 second to get that dominant color. So let me pause for a second and make sure everyone. The goal is to understand writing a chemical name or writing a chemical formula. And this is something that you could review over and over, and hopefully you can come to today. If not, it's going to be recorded and I'll post it. But this is a review of writing chemical names. And when you're writing chemical names, when you're writing chemical formulas, you want to make sure you have a periodic table handy. You want to make sure you have that. So when you're writing chemical names, you want to use a periodic table. For the family numbers, So the family numbers will guide you to write the charge values. For instance, anything in family 2A, when you find an element in family 2A, that forms a +2 or a 2+ ion. Okay. The other thing you want to use is the metal cations that have more than one charge. Okay. For instance, copper can be +1, copper +1, or copper +2. And so there are 5 metal cations and can have more than one charge. And so you need to indicate that in the chemical name. And then you also want to use the polyatomic ions list. And those are all together on one spot. There's one page in the, here, I'll show you this, is in the Chem9 homepage. I'm going back to the Chem9 homepage for a second. You've got the modules, and in the modules, at the very bottom of the modules, in the reference materials, I put all of this together on one page. So not metric prefixes, not appendix 1, not the Chem9 cheat sheet, but this one, this is a periodic table with the periodic table at the top with the family numbers. You also have the common polyatomic ions. You use those a lot in writing chemical names and chemical formulas. And then those are the 5 metals that can form more than one ion. And you need to represent which ion, say for copper, if it's 1 or 2, in the name. This is called the stock system of naming, where you have the Roman number represents the charge value. So Roman number 1 means a +1 charge. Roman number 2 means a +2 charge. And that's important because there are 2 versions of copper ion. Just like in a class, when you have 2 possible, let's say you have 2 people that are named Joe. So what do you do in a class when 2 people are named Joe? You go to an initial. There's Joe A and there's Joe B. So this is why copper has copper Roman number 1 or copper Roman number 2 to distinguish between the 2 ions. Okay, so let's go back to writing those chemical names of today's lab. Okay, but you should have that handy, especially because I'm going to see if you guys are there by giving some points away. So let's start with this is Ba and Cl2. So this is Ba, that is barium. It's in family 2, and in family 2A, they always are +2 ions. And so this 2 crossed over and down. That's why it's BaCl2. So that's barium. And then this is chlorine, which because it is the anion, it has the name ending changed, removing the last 2 letters and adding IDE. It's called barium chloride. This next one is calcium. So that's the element symbol for calcium. Calcium is also in family 2A, and that had a +2 charge that crossed over and down, and that's in the formula as a subscript. So that's calcium, also with the anion, chlorine, with the last few letters taken off and changed to IDE, name ending. This next one is copper, but it's not just any copper. So does anyone want to tell me which copper it is? And I'm getting out a piece of paper because I'm giving someone a bonus point for telling me which copper it is. Don't be shy. Nobody wants a bonus point? Is it copper? Which copper is it? Cuprous. Okay, that's Abby. So it is copper +1. Oh, sorry. Nope. Sorry. It was it's Yu Ying. It is copper 2. It is copper Roman number 2 because this 2 had crossed over and down. So it's copper 2+ with the Cl-, and that's how this became CuCl2. Sorry, Abby, you'll get another chance. So this is copper with a Roman number 2, and then it still is the chloride. Okay. All right. I'm glad you're there. Okay. How about this one though? The next one. Anyone want to tell me the name of that element? I'm going to give Abby first dibs. She got it. Okay, now I can put your name back on the list. And how about that? You're getting bonus points even before the usual Kahoot. So this is potassium. That's K. It's one of those names that existed before the process. So it's either Latin, Roman, or Greek that started with a K. I think it was Kalium. And so this is potassium and then chloride. Okay. How about this next one, lithium? I'm going to answer this. So lithium is in family 1A. Now I have a question, and this is going to be easy for someone else. Is it lithium Roman number 1? Nope. It's only the elements that those 5, the copper, the iron, the lead, chromium, and tin. Those are the only ones that are going to have the Roman numbers with them. Okay, so it's only those 5 that are on that list, those metal cations. So that's just lithium and chloride. And then this next one, this is sodium and chloride. So this is Na, that's sodium. That's also from its older name, natrium. That's why the element symbol is not just an S, but it is Na. So that's sodium and chloride. Okay, thank you everyone for participating in a little early act. All right, so let's talk about the atom. So here's an interesting thought, is that we're all made out of atoms. Everything in the universe that's not energy is matter, and the smallest unit of matter is atoms. So that's one way to think about it in a great sense, like, okay, we're all exactly the same. We're all made out of the exact same stuff, these atoms that are elements in the periodic table. If we're all made out of the same stuff, we're all made out of the same atoms, what's the atom made out of? What's inside of the atom? And so this is a model of the atom that's called the Bohr model, because of the scientist that described the inside of the atom. And there's some amazing things about this model, is that the scientist, his name is Niels Bohr, he did these experiments before there was electricity. So he did these experiments that were exactly like those flame tests that you saw me do. I did those at SMC in the chemistry lab 332. And so he basically took an element and he burned it in a flame and looked at the color. So what he did that was different, that I did not do, is he looked at that color and ran it through a prism. So I'll show you what that does in a second, but you have a prism, which is like a raindrop. And when you know raindrops in the sky will split the colors of light into component colors, so you get a rainbow. Well, when you are looking at a flame test, it's one color, mostly one dominant color, like red, orange, or yellow, green. That dominant color, when split into its component colors, gave him some results that he was able to understand and interpret. So he interpreted it into the model of the atom. So it's significant because he did this before electricity, and he did this without actually breaking the atom open. Because if someone asked me, for instance, what does it look like inside of my house? I would say, well, just come inside of my house and look at it. And so if you guys are wondering, gee, what does it look like behind her house, behind this screen? Well, you just need to come inside to look at the inside of something. Well, you can't do that for an atom. You can't just look inside of an atom. You can't cut open a little hole and make a window or a door. What would happen if you try to break open an atom is that atom busts open and releases a ton of energy, and that's a nuclear bomb. So you can't just break open an atom to look inside of it. You can't cut open a window. You can't even peek inside of it. The experiment that was done was not dangerous at all. It was that exact flame test, except for adding an additional step of looking at the colors, the color of light, through a prism. Okay. And so this model, the Bohr model, he was able to do before electricity without actually breaking an atom open. And that's pretty significant. Because honestly, you guys can't answer that. What does it look like behind the screen? What does it look like inside my house? You can't answer it. You cannot do it. But this is a way to understand the structure inside of an atom. So this is the structure. The model has electrons in energy levels. And the energy levels are these concentric circles around the nucleus. So this is the nucleus in here. And in the nucleus, that's in the center, that has the protons and neutrons. But let's focus on the protons. That's a positive charge. So putting a positive charge proton in here, this is the hydrogen atom has 1 proton and 1 electron. So I just put that 1 proton in the nucleus, and it also has 1 electron. And the 1 electron, which I can draw as a negative, electrons have a negative charge compared to protons that have the positive charge, or written as E minus like this. Okay, protons have the symbol P plus. So this is the electron right here, this little blue dot. And the electron is on that energy level, which is energy level 1. So this is called the ground state configuration. The ground state configuration is when you have the electron is in energy level 1. And this is energy level 1. And there's different ways to call this. It's 1n, which I sometimes write as E1, or it could be n equals 1. Okay, n equals 1, or energy level 1. Those are all different ways. Okay, and so that's the electron in energy level 1. That's the closest circle to the nucleus. And the electron is happy in that ground state configuration because it's closest to the proton. Remember, opposites attract. And so this positive charge will attract that negative charge. It's not going to be attracted straight in because it still has to stay on this circle. Okay, and it's moving on that circle. It's moving in a circle around on that circle. It cannot be in the space in between. It has to actually be on that line. And that's that model, is that electrons are literally on these levels like bookshelves. Okay, and so this one is the electron is in the closest to the nucleus on energy level 1. And this is the lowest energy level. So that's the structure inside. And when you have more electrons, you'll have more energy levels, and you have different elements have different interior structures, different numbers of energy levels, different numbers of electrons on those energy levels, because this is hydrogen with just 1 electron. Well, all the other atoms in the periodic table have more electrons. There's 2, 3, 4, counting all the way up to 118. So it's different structures inside to house all those electrons, but that they're considered like shelves, like bookshelves, putting books on a shelf. You have electrons in these energy levels. And so what you have in this experiment that he did is that he took the light and he split the light, that flame color, into its component colors using a spectroscope, which is basically like a prism. So we know a prism or a raindrop can split visible light into its component colors. Okay, and so we have this is the listing of the component colors of white light, which is all the colors. So you've got red down here that's low energy, and violet that's high energy, and then all the colors in between. So remember that red is low energy, and it is a low energy value for E, compared to violet, which is high energy or a high energy value for E. Well, remember, energy is related to wavelength and frequency. So a low energy means a low frequency, which means a low or a high wavelength. Those are all related. A high energy, or as a high value for E, which is a high value for frequency or a low value for wavelength. So they're all related back to the numbers that you just calculated. And so we can look at the colors qualitatively, but you can also calculate the energy values and the wavelength values and the frequency values, and they're also all related. Okay, and so what you see, for instance, when you see the hydrogen flame test, which you did not get to see, but the hydrogen flame test is kind of a pinkish color. Okay, and it has an overall absorption spectrum of this, but through a prism, or a spectroscope, so a prism is probably what Niels Bohr used, but if you used a spectroscope, which you're going to see a spectroscope example, you would see this, the line emission spectrum for hydrogen. So the component colors of that pinkish color are broken out into these lines. So there's 1, 2, 3, 4, 5 lines. Okay, so you get 5 lines of color. Okay, so you get 5 lines of color, and each of those colors is an amount of energy. So that's where Niels Bohr comes in, as he said, he looked at these colors, he looked at the pink, he looked at these 5 lines of colors that are produced when you run it through a prism. He said, how does that one electron in hydrogen produce 5 different amounts of energy? It's only one electron. How can it do 5 different amounts of energy? Well, it must be because inside of the atom are these different levels of energy inside of the atom. So inside of the atom, there must be different levels of energy. There must be a way for that one electron to produce different levels of energy. And that's because the interior structure of the atom has different energy levels. And so that's how he got to this, arrived at the conclusion that there are energy levels inside of the atom. So there are some energy levels that allow for a low release of energy. And there's some levels that allow for a high release of energy, a high amount of energy. Because we know that red is low energy versus violet, that's high energy. And this lowly one electron can do all of this by basically moving between energy levels. Okay, so let me pause for a second. Okay, so this is called the line spectrum of hydrogen. And I'm going to have you guys do this video assignment next, but this is where we're getting at, is that line spectrum of hydrogen. You can see this here is 5 lines of color, and each release of color, the colors that are seen, whether it's red or violet, they're related to an amount of energy, and an electron is basically making transitions. It's jumping between these levels and releasing a lot of energy, which would result in a violet color, or a little jump, which would result in a little bit of energy or a red color. So big jump, big energy, little jump, little energy. And in this video assignment, I'm going to point you to that in a second. You're going to be watching this video, and the process of watching the video, you will be asked questions, and the questions are part of your grade for this week. Is you can stop, you can rewind and rewatch a section if you want to answer the question correctly. You can also, after the submission, redo the whole assignment, but it's an 8-minute video with questions embedded in it. There's 3 questions that are worth points, but I think there's a total of 5 questions. So this, I've cleared what I had written earlier. This is the slide I looked at. But now we have a little picture of what's going on. When you put when you have a flame test, you're basically taking an element and you're adding energy. So you're adding energy to an element, you're adding energy to the atom. And so adding energy to the atom goes to not the whole atom. It doesn't go to the nucleus. What it does is it adds energy to an electron. And specifically adding energy to this hydrogen atom adds energy to this electron, which is in that ground state. It's in energy level 1. And so that causes the electron in energy level 1 to jump. So electron in n equals 1, that will jump. And it'll jump to a higher energy level. And so like a higher bookshelf, it can jump up to any higher energy level. And so let's put it up here. And now you have an electron that is slightly different. So this is now is an excited state. That's an excited state electron. And that's what this is in red with this is now a star. And this is a temporary state. So the electron does not hang out in that higher energy level. Why? Because it wants to go back to where it was. It's most stable in that ground state, in the level closest to the nucleus, closest to the proton, because positive and negatives attract. Why did it jump up there though? Because you added energy. So the electron will return. It will return to its original state. So it will return to its original energy level, and it can do this in some different ways. So it will return to that energy level in one big jump. So let's take it as a big jump. Let's look at this color. It can do a big jump. And this is a big jump, which is going to release big energy. Okay, a big amount of energy, which would be related to a color, or it can do this in a bunch of different jumps. Each little jump, a little jump is going to release a little amount of energy. And so those are those transitions between energy levels. And that's how there are energy levels in the first place. There are energy levels within the atom. Music. It's not mine. Okay, so here we have, going back to, this is on your lab procedure. This is showing these examples of transitions. Electrons are in those energy levels, and this is the nucleus. There's the positive proton in the nucleus. What happens when you have this is a big jump. This is a big amount of energy. And so this is a lot of energy released, would give you a high energy color like violet. And this would be a small jump. This would give you a release of less energy. A low energy color would be the result, like red. Okay. And so it's these transitions that electrons can make inside of an atom that allow for those different colors that are seen as what are called the emission spectra. So you have these for each of those flame tests. I could have taken each one of those colors and not just looked at the color, but also looked at it through a spectroscope and seen the lines, the component colors that color is. So what is the actual sodium is just these two lines of color. So sodium was that big yellow flame. So when you look at the component colors, it's this yellow lines. Compared to helium, we didn't look at, but it has these 1, 2, 3, 4, 5, 6 lines of color. That tells you something about the energy levels, the architecture inside of the atom that you can't see. And so the line emission spectrum, this is like a fingerprint for a human. These can be used, so like fingerprints for humans, you can use to identify each individual human. Each individual person has their own individual unique fingerprint. So it can be used to identify any individual human. Well, the line emission spectrum can be used to identify elements. And this is by the colors of the light that is emitted. So for instance, you can take your telescope and look at Venus or Mercury, or even stars that are light years away. You can look at the stars because they're emitting a light, and you can look at it and say, okay, that's far away, but you can get some information about that star or about Venus or about Mercury by then running that light through a prism and splitting it into its component colors. And if the component colors look like this, where you get these lines of light, then you can say there must be helium on Venus. Or if you get something that looks like this, these component colors of the light, there must be neon on Venus or Mercury. Is that it named Mercury because it has this component color, this line emission spectrum? No, it has to do with the temperature. But the Mercury has a line emission spectrum that can be basically used for any faraway planet, light years away. You can figure out what the elements are on that faraway planet by looking at the light from it. And so that is called the emission spectrum. So you guys got to see the hydrogen line emission spectrum. Okay, let me pause. You want to list the unknown and the known information, and then that will help you find the equation that you're going to use. The equation needs to have the unknown and the known. And so the equation that has both of those is this one, C equals wavelength times frequency. But the thing is what you want to solve for, which is the wavelength this time. This is wavelength. It is not isolated. It's not by itself on one side of the equal sign. So I first want to isolate the unknown, which is wavelength. So this is that symbol, the upside down Y, lambda. So this is going to be C equals wavelength times frequency. And this time what I'm trying to get rid of is, switching to here, I'm solving for this. And I want to get rid of frequency this time. So I'm going to divide both sides by frequency. So this will get rid of that on that one side. And what you're left with then is the equation that you're going to use, which is wavelength, the symbol lambda, equals C over frequency. Okay. Now, the other thing I want to point out, this is just getting you started, is that Hertz, remember Hertz is this units. So Hertz is not useful. What you want to write this as is one of the other versions, and the most useful version is the 1 over S. So instead of writing this as Hz, you want to write this as 4.3 times 10 to the third 1 over S. Okay, so that's the frequency that you're going to want to plug into this equation. Don't plug it in as Hz because it's not going to cancel out. So you want this unit. These units will cancel out. And so when you're looking at those units, you also want to make sure there's not a metric prefix. Like in the examples that I did earlier, metric prefixes will also not cancel out. So that should get you started on this one. You also want to remember to round to sig figs. So the original number has 2 sig figs. So you want to make sure your answer will have 2 sig figs. This is the measured value. Okay, don't ever look at the value for C, which is a constant, and it is infinitely significant. Same with the Planck's constant. Don't want to look at any of those constants for the sig figs. And you also want to make sure you put your answer into scientific notation. So let's take a preview of this next one. So the next one is calculate the energy. So the first thing that pops out is the unknown again. You want to solve for energy, which is E. So you want to write the variable E. You don't want to write the word E. You want to write equals E, because the variable E is what you're going to be looking for when you're looking for an equation. So then reading this, it says when frequency is 900 MHz. So this is known information when they give you the number and they tell you that it's frequency. But again, you want the symbol for frequency, not the word. So you want to write that cursive V. Okay, so that's new, the symbol for frequency. And then what it is equal to, which is 900 MHz. So M is the metric prefix mega. That's 10 to the 6th. So instead of writing 9 MHz, those units will not cancel out. So these units, the M and the HZ, will not cancel out. So what you want to write is 900. And then instead of mega, you can write 10 to the 6th. Okay. And then instead of HZ, remember HZ is 1 over S, you want to write 1 over S. And that, remember, is your value for frequency. So in looking for an equation to solve for energy, you need E and you need frequency. So this is the equation that has both of those. Okay. So you also have to remember that you always have H. H is Planck's constant. Just like above, you always have C. That's the speed of light. And you know where you can find those. They're in the lab procedure. There are a bunch of places. Okay. And so this number value is the number you're given is 900 megahertz. When rounding the answer, you want to make sure you go back to this number value. And this number value, 900 megahertz, has only 1 sig fig. So your answer should have 1 sig fig. And you should also make sure you put that answer into scientific notation. Okay. So looking at number 3, preview of number 3 is you've got, this is a high band 5G cellular network, uses a frequency. So the first thing that pops out is unknown, is your frequency. And the frequency is that symbol nu. And this is the number value 25 GHz. Okay, so what's G? G is the metric prefix giga. And you don't want to just write it as G, you want to make that, get rid of that metric prefix. Giga is 10 to the 9. And then also HZ, you don't want HZ because that's not going to cancel out. So you have 25 times 10 to the 9, and instead of HZ, 1 over S. So continuing on, you want to calculate the wavelength. So that's the unknown, the thing you're trying to solve for. Calculate the wavelength. Wavelength, the word, is not as useful as wavelength, the symbol. And that will help you then find the equation to use. The equation you're going to start with is the equation that has both the symbol for frequency and the symbol for wavelength. That's this one. C equals wavelength times frequency. But make sure you first isolate the unknown. That's going to be the thing you're trying to solve for is wavelength. And you're going to have to isolate that and in order to solve for it. Okay, you're also going to need that value for C. That's the speed of light, and that's a constant. The answer, when you are rounding it, you're looking at the 25 gigahertz has 2 sig figs. So make sure you round your answer to 2 sig figs and also put it into scientific notation. And then continuing on to, this is number 4, which is the same radio station above. You have the same information as before, but now the unknown is different. The unknown is energy. So instead of energy, the word, you want energy, the symbol, E. So what's the information is the same information as up here. You still have the frequency. So you're going to use this frequency. That symbol, which is frequency, will then help guide you to what equation to use for this one. Okay, so it still has the same number of sig figs in the 25. So you still need to round to the same number of sig figs for the answer of the next problem number 4, and also put your answer into scientific notation. Okay, so that should get you set up to work on all those problems.